So, we are going to talk about superconductivity. So, having seen various phenomena in condensed matter physics such as magnetism, then metallic behavior, insulating behavior, ferromagnetism, antiferromagnetism, and doing a thorough analysis with regard to the Green's function. Let us now talk about superconductivity, and initially we are going to give you a glimpses of the historical achievements of superconductivity, that is how it got developed in the earlier years, and also will try to give you some recent experiments on superconductivity, which are not very recent, but still compared to the time that it was discovered, there are some recent developments. And then we will talk about the most important thing, which is called as a BCS theory, the microscopic theory about superconductivity. So, in these few slides we have tried to first give you the outline and then discuss with a little more details, and let us look at the periodic table and which are the superconductors, or which form or which has this phenomenon of superconductivity, which is vanishing of electrical resistance below a certain temperature, certain characteristic temperature, which is a characteristics to that particular system. If you look at it, there are examples of superconductor. The first superconductor was in mercury, and they are in lead and in tin and in indium, antimonide and so on, and also some thallium based compound, and in aluminum for example. And so, there are examples of superconductivity here. So, if we nicely split the periodic table into two halves, the superconductivity occurs at the right half of the periodic table, whereas the left half, if you see that they are nice magnets, I mean including these are nice magnets, and there are superconductors which are denoted by the circles. So, superconductivity in the earlier days have been seen in these materials, and from the color code that is presented in this periodic table, there are basically basic metals they form superconductors, and there are these are somewhat like transition metals and semi metals and so on. However, both the magnets and the superconductors, they have a lot of electrons at the Fermi level. However, in magnets, the wave function of the electron, or the the range over which the electrons electronic wave function are distributed have a certain range, whereas for the superconductors the range is quite large, and that is what pretty much distinguishes metals, or rather the magnets or the elements which show magnetism with the ones that show superconductivity. So, let us go ahead with this, and let us talk about a few books that are of importance. One can look at books such as Tinkham is a very good book. Mahan we have already been talking about. There is a book called Tilly and Tilly, their book called by David Spines. J.R. Schrieffer, one of the discoverer of this BCS theory, and there are numerous review articles on superconductivity which you might want to have a look at it. So, these are our starting point, and let us have a historical overview. Superconductivity was discovered in 1911 by a gentleman called Kamerlingh Onnes in Leiden. That is the name of the place. This is in Europe, and so after 3 years he had liquefied helium to reach temperatures of the order of a few Kelvin. Now, why are they related or they have been placed one after another is that it is important to achieve low temperatures in order to see superconductivity. Superconductivity does not occur at any temperature or at room temperature, it happens at very low temperature. So, one has to cool a system, a metal so to say, to that temperature below which it shows superconductivity, and it is intimately related to the liquid helium temperature, which is why it is mentioned, which is about 4 Kelvin, 4.2 Kelvin. So, a liquid helium temperature is needed in order to cool a system, and that is why the superconductivity, discovery of superconductivity is also intimately related to the ability, to our ability of achieving low temperatures. Then the microscopic theory, which is known as the BCS theory, goes after the name, we will talk about this, Burdin, Cooper and Schrieffer, that was given out in 1957, which is just about 60 years back from now. And then a new class of superconductors were actually discovered in 1986. They are called high temperature superconductors. So, the superconductivity in these conventional materials which are seen above, in the sense that discovered by Kamerlingh-Onnes, and then a few years the researchers have dealt with superconductivity around with at most transition temperatures to be 20 Kelvin. So, below 20 Kelvin they showed superconductivity, and above that the superconductivity was discovered. By the way, the Kamerlingh-Onnes saw superconductivity in ultra clean mercury samples, which had shown a sudden drop in resistivity at certain temperature, below certain temperature rather, and within a very small narrow temperature range. So, this was about 1986, and then early 2000 there are other superconductors which are based on iron. So, iron and superconductivity, they do not seem to go hand in hand, because irons are supposed to be ferromagnets, good ferromagnets, and the ferromagnets imply that there are the spins are all pointing in the same direction. That is what ferromagnetism is about. However, a superconductor requires a pairing of up and down electrons. I mean, two electrons, one having an up spin with a momentum k and the other with a momentum minus k and a down spin. So, apparently there is an ambiguity, but there are instances and experimental evidences of iron based superconductors. So, what Kamerlingh-Onnes did is that while he was doing an experiment with ultra clean mercury and then subsequently with lead and tin, we have shown in the periodic table that there are lead and tin etcetera showing superconductivity. So, the electrical resistance that disappeared completely in a very small range of temperature. We have some supporting figures for that, you will see, and that particular temperature below which the resistivity vanishes is a characteristic of that particular material, and the complete disappearance of the resistance is demonstrated by the existence of persistent currents that flow in superconducting rings without any decay for a year. And in fact, the nuclear resonance experiments have predicted that they would only be decaying in a time scale of 10 to the power 5 years, which is, this is like 10 to the power 5 years, and that is why they are called as perfect conductivity. Now, this word also has to be taken with caution, because very good metals have perfect conductivity, or rather infinite conductivity as T goes to 0, the temperature goes to 0. However, they are different from superconductors in the sense that perfect conductors do not show a property called as Meissner effect, which is said later, and superconductors show this property of Meissner effect, and superconductors show perfect diamagnetism, which is again what was discovered by Meissner and Oxenfeld, and this is something that we are going to discuss. This is the electromagnetic properties of superconductors, which are very important. So, superconductivity can be destroyed. Why we are talking about destruction of superconductivity is that then we understand how robust the superconducting state is. So, it can be destroyed by two means, that is, one is thermal effects, that is, if you raise the temperature of the system, or if you apply an external magnetic field. Both these can actually destroy superconductivity, and the system will go on to a so called metallic state. It does not have to, we will see that in high TC superconductors they do not go on to a state which is exactly metallic, but there are some deviations there as well. In any case, so there is a critical temperature and a critical magnetic field that exists below which the superconductivity is robust, and above which superconductivity vanishes, which means that we have a metallic state that emerges beyond that. So, once superconductivity is destroyed, there is a emergence of a metallic state. So, we are going to be concerned about mainly two aspects of superconductivity, and one of them being the electromagnetic response, as we have just said, which takes care of the Meissner Oxenfeld effects and so on. And this was discovered by, or rather they are described by London equations. We will give us a small overview now, and then we will do it later in an elaborate fashion. And then also we would be concerned about the microscopic theory of superconductivity, which is known as BCS theory. And you will see that how it was actually Cooper's problem, it is called Cooper instability. It is shown that two electrons which are known to be having the same charge and hence would repel, they can be shown that they actually have an attractive potential operative between them when they are in presence of a filled Fermi sea. Okay. And this attractive interaction is mediated via phonons. So, also we may talk on the phenomenological theory of superconductivity, which are known as Ginsburg Landau theory. So, these phenomenological theories in general are very good starting points when microscopic theories are unavailable, and they provided you take into account the correct symmetries of the problem, and you know that how a system loses superconductivity, then you can write down a free energy function in terms of some wave functions, or rather some order parameters, which are going to give you particularly the phase transition is captured by writing down the free energy functional in terms of the order parameters. So, a very brief description is first presented about each one of them, and then we will go on for a little elaborate discussion. So, to start with, it was we said that it is electrodynamics. So, these were by two brothers F and H London, F London and H London in 1935. So, they actually wrote down equations where the electric field and the magnetic field variations inside a superconductor can be described in terms of the number density of the superconducting electrons or the supercurrent density. So, it is important to say that normal current does not flow through a superconductor. because of this superconductors being perfect diamagnets, the normal currents will be killed and they cannot penetrate into the superconducting sample, whereas the super currents, what we actually mean by super currents will be explained later, they can be they can propagate, or rather they flow in the superconducting sample. And it nicely yields, starting from these equations which are nothing but some variations of the Maxwell's equations of electrodynamics, one can get diamagnetism from and hence Meissner effect. This is what we have talked about. Then we have this microscopic theory that should come into the discussion, which was again put forward in 1957 by three people called Burdeen, Cooper and Schrieffer, and the superconductor. So, it will show that how the energy gap in a superconductor varies with temperature. So, what we mean by an energy gap is that there is a ground state and there is a there is an excited state where superconductivity is basically destroyed. So, when the system is in the superconducting state, the ground state becomes occupied by all these pairs of electrons. So, they form pairs which are actually pairs of up and down electrons, and then there are many of these pairs that are present, and the ground state is actually a many body ground state of all these pairs. So, there are soups of pairs, and in order to break a pair, we can populate this the first available excited energy level by breaking the pair, and that breaking can be done, as we have said, either by applying temperature or by the magnetic field. So, how do these electrons have attractive interactions? We have already said that, uttered that the interaction is mediated via phonons, they can still have attractive interaction. And these BCS theories, they properly explain the thermodynamics and the transport properties, such as the vanishing of resistivity below a certain critical temperature. And then the Ginsburg-Landau theory, as we told, it is a phenomenological theory. It does not have any microscopic basis, and it was put forward ahead of BCS theory when BCS theory was unavailable. And what it did is that it wrote down the free energy functional in terms of powers of the order parameter, or basically the complex wave functions that describe a transition from one state to another. So, it concentrates on the superconducting electrons and not on its excitations. It is based on the Landau's general theory of second order phase transition, that is why this name Ginsburg-Landau has come in. And in terms of free energy so free energy is a functional of the order parameter. So, one has to identify the order parameter and know that how it vanishes at the phase transition, then one can write down a free energy functional and do calculations of say electrodynamics, and it also very importantly introduces two length scales of the problem that distinguishes type 1 and type 2 superconductors. We will see what are type 1 and type 2 superconductors. So, broadly all these conventional superconductors which were discovered before 1986, they all can be plugged into one or the other type of superconductors. And so, let us go to slightly more elaborate discussion of superconductivity. So, it is this gentleman which we said H. Kamerlingh-Onnes, and he was working with very clean, absolutely clean mercury, and he found that the resistivity above 4.2 Kelvin, it has a linear behavior here, and suddenly in the vicinity of 4.2 Kelvin, in fact, within a temperature range that is very narrow, it is of the order of 10 to the power minus 5 Kelvin. It does not show it that way, but it is true that there are so this fall off is extremely sharp, and so below 4.2 Kelvin the resistivity becomes so small, almost negligible. So, of the order of 10 to the power minus 5 ohm. So, the left of this transition is called as a zero resistance state, and this is a Marcury, the plot is that of a Marcury showing transition, T c being which is the temperature that demarcates a metallic regime and a zero state regime is that temperature is 4.2 Kelvin. So, what happens is that there is a sudden loss of electrical resistance. Electrical resistance is denoted by the symbol rho below a certain critical temperature T c. There are very sharp superconducting transition, as we have said. The magnetic fields are completely expelled from superconductors. So, if there are magnetic fields that are going to be completely expelled from the material, from the specimen, and they cannot enter other than a very small depth of the specimen, which are called as penetration depth, we will see that. And that is why, because there is absolutely no magnetic field, so that is why they are called as perfect diamagnets, which the diamagnetic susceptibility becomes equal to -1. So, m by h limit h tends to 0. So, this is the susceptibility is defined as m by h in the limit h tending to 0. This becomes equal to -1. So, m and h are actually oppositely directed, and this is the definition of perfect diamagnetism. In even the best of the systems that show diamagnetism other than the superconductors, the or rather the chi is really small, it is of sometimes of the order of 10 to the power minus 4 or 5. However, in superconductors it is equal to 1. Then, as we have said earlier, that there are lossless energy conduction and generation of strong magnetic fields. So, in the vicinity of the superconductor, there are generation of very strong magnetic field. We will show you at the end a video showing that how magnetic field is expelled, and Japan is actually making a train which would be realizable around 2027 or 2028. These are called as the maglev trains. And this maglevs is the short form of magnetically levitated. So, let us see that what happens for a good metal and a superconductor. In a good metal, the resistivity decreases, and as t goes to 0, it takes it gives you a value which is finite. So, this is r equal to r not equal to 0. Whereas, for a superconductor it decreases and then it suddenly drops to 0 at a temperature which is equal to T equal to T c. So, that is the basic difference between good metal and a superconductor. So, there are several things that one had to take care of in experiments, and so Kamerlingh-Onnes felt that the cold wires resistance also would dissipate. So, this suggested that he would there would be a steady decrease in electrical resistance, allowing for better conduction of electricity. Okay. And then Onnes passed a current through a very pure Marcury wire and measured the resistance as he steadily lowered the temperature, and that is how the experiment went off. Much to his surprise, he saw that there was no resistance at 4.2 Kelvin, implying extremely good conduction of electricity, and this is the discovery of superconductivity. So, the question is, why is resistance 0 in a superconductor? electrical resistance is caused by electrons that lose energy by scattering between or with each other. So, there are new channels in which the energy can be dissipated that opens up, and because of this scattering between electrons, the energy dissipates. The electron pairs are all in their ground state and hence cannot lose energy. For superconductors, the electron pairs they form pairs and they go into the ground state. So, there is no way that they can lose energy. So, the superconductivity is a phenomenon of the ground state. However, the need to acquire at least a kinetic energy equal to the energy gap to lose energy by breaking a pair. So, there are you need to give it an energy, a kinetic energy such that the pairs dissociate and they break, and there are some electrons that are made available in the excited energy state. The question is that is the resistance really 0? The experimental answer is that a lower limit of what we have said already, 10 to the power 5 years is established for a decay time of current in a superconducting loop, which is 10 to the power minus 5 precision over a year, which is an extremely good signature that the resistance is really equal to 0 and the current is really persistent. So, we have said this, that what kills superconductivity? So, we need to provide enough energy for the pairs to dissociate, and the pairs remain within the coherence length of each other. So, there is a thermal energy that can be given, and there is also a critical current density. This is something that we have not said earlier. There is also a critical current density which a superconductor can hold, and there is also a critical magnetic field which is needed for it to the break superconductivity. So, T c, J c and H c are the critical values demarcating a superconducting state from a non-superconducting state. So, that the question is that what drives superconductivity? What causes a superconducting transition? So, the density of states at the Fermi level, call it DEF or NEF depending on which book you are following. So, the density of states at the Fermi level plays a critical role. These are the most unstable electrons in a solid, unstable because they can actually cross the barrier and go on to energy levels that are available to them, whereas the ones that are actually much farther away from the Fermi energy are very robust, they do not make any transition. So, these unstable electrons, they can easily rearrange themselves to lower their kinetic lower their energies. So, electrons near the Fermi level are able to lower their energy when the superconducting gap opens up. So, these electrons in the vicinity of this thing can actually lower their energies, and so this is like acting like a refrigeration, because so when there is a superconducting gap that opens up. So, what we are trying to say is that it is only the electrons in the vicinity of this can move into the gap, and the other electrons they do not make any transition and make any attempt to go and occupy other energy levels. That is, there is a selective cooling, which are the most energetic electrons that are near the Fermi surface, and these electrons are actually going into states which are occupied, and thereby causing cooling to the rest of the system. So, this is one typical this thing called diagram called as for the T greater than T c, it is for a normal metal, where we have plotted the density of states on the x axis and E on the y axis. In a lot of other books you will see that these axes are interchanged, but they carry the same meaning. And for a superconductor, there is a Fermi energy, at the Fermi energy there is a gap that opens up, and that gap has to be accessed, or rather it has to be overcome in order to have the electrons going into the normal state, or rather the superconductivity is destroyed. And this corresponds to a gap which is given by the metallic gap, or rather the gap that we see in usual cases. So, this is the gap energy, and we need to get over the gap energy, or rather supply larger energies than the gap energy in order to destroy superconductivity. So, each electron gains delta and a pair gains 2 delta, and so the number of electrons that are involved in this process is half of E g, because this is for the twice of the gap, and then multiplied by the density of states at the Fermi level. So, these are the number of electrons that are available for causing superconductivity in a sample. So, what are the experiments which see superconductivity or sort of make inferences about superconductivity? They are infrared absorption, which does the measurement of the energy gap. They are tunneling, which do the measurement of the superconducting density of states, and show these that a superconductor has a gap that appears at the Fermi level. Photoemission tells you that if there is a momentum dependence of the gap, whether the gap is homogeneous at all k values, or there is a particular fashion, or rather an orientation in which the gap is smaller along some direction of k, or it is bigger in some other direction. NMR it probes short pairs. So, usually these pairs are defined by a coherence length, which is basically the resulting the size of the resulting wave function, and there are also smaller pairs. In fact, this high T c superconductivity is caused by, or it is believed to be caused by, shorter pairs. So, NMR probes this existence of shorter pairs, and of course, XRD, which is X-ray diffraction, it does the crystal structure determination of all materials including the superconductor. So, we will see this magnetic levitation in a video that we have said, and this is one of the properties. Now, how does the magnet levitate in presence of a superconducting sample? Because there is a very large magnetic field density in the vicinity of the superconducting sample. That is because the magnetic flux is very large in the vicinity, because all the magnetic field lines are pushed out of the superconductor and they bunch together, so much so the magnetic energy is able to lift the weight of such a disk or a ring. Superconductors also have electronic and magnetic properties. So, that is we already have said that they have a negative susceptibility, and they acquire a polarization opposite to that of the applied magnetic field, and that is why the superconducting materials and magnet, they actually repel each other. So, this is the reason for that. If the temperature increases, the sample would lose its superconductivity, and the magnet will not be able to float on the superconductor, because superconductivity is destroyed. So, the Meissner effect goes along with that. So, there will be no more exclusion of the flux, and so the magnetic energies go away, which used to support the weight of the ring. This is in this cartoon, there is a sumo wrestler which is shown that he is standing on a platform, and the platform has a small gap as it is shown here between the ground and that. So, the superconducting platform. So, because this plank or the layer of the material on which the sumo wrestler stands is shown here, this one, the top one, and the bottom one is a superconducting sample. So, this levitation can actually support the weight of a sumo wrestler. This is what is being said in this diagram. And this is the maglev train, which is not yet operational, but they are planned to be operational. They would reach velocities more than even the bullet trains, and the reason being that they would be levitated and they would not be having any superconduct or any friction from the rails which usually impede the velocities. These are nice looking trains, and they are probably artists' impressions of how the trains are going to look like. And this is, of course, some of them are only our futuristic ideas and ambitions that we will have, that there are large scale applications of superconductors which can begin to appear, like American superconductor, 2G wires. So, there are YBCO, that is yttrium barium copper oxide, and Y2O3 yttrium oxide nanoparticles for flux spinning. One can have the superconducting power cables such that there are persistent current and you do not have to sustain the current. One starts, it will keep going on, and various other things. I mean, there are weight reduction of the wind turbine, 10 megawatt generator which will weight 120 metric tons instead of 300 using conventional copper wires and so on. And these are the applications which we can see in the future. There are medical applications. So, these ones are actually superconducting magnet coils which produce very large uniform magnetic fields that can penetrate through the patient's body and will give information if there is an anomaly or there is a pathological defect in the human body, and then the actual treatment can proceed. A lot of medical diagnostics are now dependent on MRI, doing MRI, and so they crucially have a lot of applications in the medical sector. So, to talk about those important developments and some dates, etc., 1935 a London brothers proposed these equations on E and H, and these are called as the London equations. 1950 Ginsburg and Landau proposed a phenomenological called as the Ginsburg-Landau theory. 1957 is a BCS theory, microscopic. It is a variational theory and cannot be obtained by doing any finite order of perturbation theory. 1986 is Bednorz and Muller discovered superconductivity at high temperatures, and then there are a lot of other, like the iron based superconductors are called as the Nictide superconductors. They are being discovered, including the magnesium boride and the arsenide, and now one is talking about the topological superconductors. So, pictorially what happens in the Meissner effect? We will do all these calculations as we go along. So, the Meissner effect, it was discovered by Walter Meissner and Robert Oxenfeld in 1933. So, this is the total expulsion of the magnetic flux. So, that is why the superconductors are called as the perfect diamagnets. Applying a magnetic field to the superconductor by replacing the magnet above it creates a surface current that produces a magnetic field to perfectly counter the applied field. So, this is T greater than T c, so the magnetic fields penetrate. As T is lowered below T c, it becomes this blue ball becomes superconducting, and this it starts repelling the magnetic fields, and now you see that in this region there is a large flux of the magnetic fields because it is bending around the obstacle. And this as it says that what happens is that it creates some surface currents, and the surface currents produce a magnetic field in a direction that exactly cancels the applied field. So, let us have a distinction between the perfect conductor and the superconductor. So, this is a superconductor. So, it is a superconductor or rather let us start with 1. So, it is a conductor, upon cooling it becomes a superconductor. If you switch on the magnetic field, the magnetic fields get expelled, and these are called Meissner effect. And the magnetic field if you so if we relax, that is if we raise the temperature. So, this is raising temperature. So, superconductivity is destroyed and the flux lines will penetrate. Now, what happens for an ideal conductor? If it is an ideal conductor, the magnetic field is on. So, it is cooled, the magnetic field is on, the magnetic field is off, the flux lines completely vanish, and if it is put in a magnetic field, then the magnetic field will penetrate. If you cool, the magnetic fields will still penetrate, and when we switch off the magnetic field, then for an ideal conductor we will have these things will make circles, the magnetic field lines will make circles, whereas this step is different than what we have for superconductors. So, superconductors it completely so if we switch off the magnetic field, then we do not have such trapping of the flux lines, and that distinguishes a superconductor from an ideal conductor. Now, there are two kinds of superconductors we have already said, type 1 and type 2 superconductors. So, type 1 superconductor is that they are pure metals, which is what we have seen in the periodic table. They are perfect diamagnets and they have lower critical field. So, the M versus H diagram, which is called as a phase diagram of superconductors, it as you increase H, the M keeps going linearly, and then suddenly it drops as you further increase H. So, as we know that if we apply magnetic field, superconductivity is destroyed, and then it gives rise to a normal state. So, this is the superconducting state inside, and there is a normal state here. So, this is another sort of this thing for how the magnetic field falls off inside the. So, this is the distance inside a superconducting material. So, it falls off, magnetic field falls off within a length scale lambda, whereas the wave function actually grows like this. So, this is called as xi, this length is called as xi, and this length is called as lambda. As you can see, this length is called as lambda, and this is called as a penetration depth, and this is called as a coherence length. So, one can actually talk about a single quantity kappa, which is a ratio of xi by lambda by xi, where kappa less than 1 by root 2 gives you a type 1 superconductor, whereas kappa greater than 1 by root 2 gives you type 2 superconductors, which means that if lambda is less than xi, so lambda by xi less than 1 by root 2, which means lambda is less than xi over root 2, then we have a type 1 superconductors, and if the lambda is greater than xi over root 2, there is a root 2 there, then we have a type 2 superconductors. And similarly, the magnetic field versus temperature shows that this the regime bounded by the red line is called as a superconducting state, and above that which is a normal state. So, there is a Tc beyond which superconductivity destroys, and there is also a Hc beyond which superconductivity destroys. And so, these are type 2 superconductors. It occurs in alloys. So, it is a combination of different elements, it is alloys or intermetallic compounds, and they exhibit a much higher Tc. So, the phase diagram is not exactly like what we have seen here. Here it is dissimilar, and there is a linear increase and then there is a fall off like this. Inside is a superconducting state, a part of it, but a part of it what is called as a vortex state, and beyond that is a normal state. So, what happens is that the magnetic field can partially penetrate into the sample, and beyond that, when the magnetic field is increased beyond that, superconductivity is destroyed. However, the magnetic flux lines that get trapped, and this trapping also happens in some nice regular ordering, and in particular it happens in form of a hexagonal lattice which is called as the Abrikosov lattice. So, this is the lambda and this is the xi, and now you see that it penetrates much larger into the superconducting sample. So, this d is the distance inside the superconducting sample, whereas the wave function of the electrons are smaller. And this is a typical diagram showing that there are superconducting rings, these are superconducting rings, and there is a magnetic field lines that are applied, and so the current supercurrent goes in these superconducting rings, or in a ring fashion the current actually circulates in about the magnetic field lines, and these are the experiments demonstrating persistent current. So, finally, just a small glimpse of what came from Burdeen, Cooper and Schiffer. So, these are the photographs of them, and this explains superconductivity at low temperature for all conventional metals, and it was started with Cooper's work. He realized that the atomic lattice vibrations were directly responsible for causing attraction among the electrons, which allow them to pair up into teams, pairs that is, that pass all obstacles which cause resistance. So, when an electron pairs up with another electron, forms a bound pair, this bound pair seamlessly move without having any resistance, or rather without having any collision, suffering any collision from another pair. So, this team or the pairs of the electrons which are called as the Cooper pairs, they move without any resistance through the sample. The features of BCS theory: the first, microscopic theory, it works well for low temperature superconductors. It is variational and non-perturbative, we will say all that. So, no small expansion parameter. The superconducting gap is non-perturbative. The predicts Tc for materials under 20 Kelvin. The phonons are essential components of the theory. London's electrodynamics is explained. Meissner effect is included at the linear response level. So, there is a tremendous success including all these things. Just to make the discussion, ongoing discussion a little more interesting, there is an analogy of dancing room scenario that was given by Schiffer, that there are these males and females pairs that are dancing on a dancing floor, and they are completely unmindful of another, and they keep dancing without suffering any collision from each other. So, there are a large number of them, and they can they pass on without suffering any collision between each other. The superconducting ground state is exactly like that. We can talk about this in details later, we will do that, but it is just that there are so these electrons actually can form a pair in presence of phonons. That is what is said here. We will come to this. Similarly, these ones, and these are some of the superconducting transition temperatures that are listed here for materials which are like tungsten, mercury, sulfur based organic superconductors, Nb3Sn and so on. So, you see that suddenly from 23 to 40 there is a large jump, and from of course 40 to 92 there are large jumps and so on. But this is that these are these high Tc. So, high Tc superconductors. This is how the transition temperature has increased since 1908. It was going fine till about 1986. This is where 1986 is, then it shot up and went all the way up to 164 Kelvin. So, there are arsenides which are discovered around this time. These are the people who discovered this Bednorz and Muller, these high Tc superconductors. They actually got a Nobel Prize in 1987, and there are still no theory because of a number of reasons. One of them being that the normal state is not known, pairing is not phonon mediated, experimental data contradict each other, coherence length is too short. There is something called a pseudo gap. It is like a gap, but it violates other properties of an energy gap. There is no controlled expansion parameters and many others, and that is the reason that even the best of the minds working in the field have not been able to come up with a general consensus that what the theory that should be there, which would explain all experiments. And if one looks at the phase diagram, which is a temperature versus doping. So, this doping gives the holes which are rather the carriers of superconductivity in this case. There is a superconducting dome that is here, but as you go up, you go into a place which is most of it is not known, and that is the reason that the theory is not known, whereas in BCA superconductors all these form nice metals which are pretty much here. So, had all these area here would have been like the Fermi liquid, we would have already had a theory. These are some layered structures of these high Tc. So, basically the essential ingredient is a copper oxide plane in all these things. So, it has a Tc of about 40 Kelvin, 77 Kelvin and 135 Kelvin. There is a lanthanum strontium copper oxide. This is called YbCO, this is called LsCO, this is called YbCO, this is a yttrium barium copper oxide, and this is called BISCO, it is a bismuth strontium calcium copper oxide, and so on. So, let us show you some cartoon for for the levitation and magnetic levitation in lab experiments. And so, this is a superconducting sample, that black thing, and now there is a coin like thing is kept there, it is kept on top of it. Now, this superconducting specimen is just a metal. Now, there the temperature is being lowered by liquid helium or some other coolant. Now, it became superconducting. Now, you see placing it on top, it is just floating. This is called as superconducting levitation, and it is simply levitating, and if you just move it, it still does not fall off onto the material. So, this black thing that you see is a superconductor now, because the temperature is lowered, and you see there is no trick there. So, it has been there is a film has been swiped in order to show that there is nothing there. So, and now it is spinning also, it is still floating. As you try to bring it closer, it gets repelled, because the magnetic flux lines that has enough magnetic energy in order to support the weight. Now, because it is kept in a kind of open container, the temperature is being raised, it lifted that thing itself, the material itself, and now you have taken it out. Slowly the superconductivity is destroyed and Meissner effect is gone, the flux are no more expelled, and the material just falls, crashes on top of the superconducting specimen. So, this is the direct lab demonstration of Meissner effect.